Good afternoon or morning, everybody. I hope you're doing well. Please excuse me if I'm a little bit out of it today. I have a fever close to 102. I'm going to keep recording anyway, but I might be a little bit slower or space out a little. For that, I really do apologize. So, without further ado, let's get underway with today's topic. Now, please pay attention. I know this is a video, so you can rewind and you can rewatch, but today's topic is a rather difficult one. One of the advantages to me recording this is you can rewatch it. One of the disadvantages is you can't ask immediate questions. So I apologize for that. Again, send me an email or post a comment even mid-video, and I will try to answer in a timely fashion as long as I don't have a lot going on here, which I might. And if you really feel like you're having trouble, please try to set up a Zoom call after school. So, today I'm going to start a topic I was a little hesitant to start, only because it can be a little bit confusing, but I think you guys can handle it, and I'm going to teach it in the simplest way possible. We are going to talk about... I think my tablet here turned off. You know what? It died. I do have a charger right here. Let me just plug that in and we'll keep going. I will have to unplug the wireless tab for it, but it will charge and be in its wired mode, so that is all right. I hope everybody is having, again, like I said, a great day. Alright, that still works. Oh, and as a quick fun fact for the day, let me think of a good one. If you look on the side of a bottle of alcohol, you will see the word proof, percent proof, or rather you'll just see the word proof, or PRF. This is the amount of alcohol that is in that bottle. 200 proof is 100%. So the question is, why is 100% not 100 proof? And the answer actually comes back to taxes. In ports, especially in England, I believe, people would import alcohol, and if it was above a certain percentage alcohol, they would have to pay an extra tax. They would report the percentage that it was, but it would also undergo a test. So at 100% proof, right, it would be more alcohol than water, and it would burn. So, and it would burn quite easily, right? They would be able to do a quick test, putting a quick flame onto it and see how fast it caught on fire. And so that's where the proof came in. At 100% proof, they would have to pay more in taxes. So today, if you want to know the percentage alcohol, just double the proof. 50 proof, right? Sorry, cut the proof in half. 50 proof would be 25% alcohol by volume. And pure alcohol would, of course, be 200 proof. All right, time to talk about the electron shell model. This is our modern theory of what an atom looks like. So, right, what we have previously talked about for an atom is, one, just a vague idea of small particles. This was proposed by Dalton with his atomic theory. After that, we go into another scientist, an extremely, extremely important one, called J. Thomson. He is the inventor of the field of mass spectrometry and I am a former mass spectrometrist, so I am a bit biased, he discovered plasmas, and he also discovered the electron. He is an extremely important chemist and physicist, and it's hard to understate his importance. He actually held the same chair that Sir Isaac Newton did. So, J.J. Thomson discovered electrons using a complex setup we won't go over, and he thought that atoms were something like a plum pudding. So a plum pudding, I can show you what that is in a second, actually, up here. Plum pudding. So here with the plum pudding, you can see it's a fairly consistent structure with small plums scattered throughout. This is how he viewed the atom. Sorry, that is for later. He envisioned that the stuff that was making the positive charge, because he figured out if there was a negative charge, there had to be a positive charge, because atoms weren't negative. Right? He thought the positive charge was all spread out through the whole atom, taking up all the space, and that electrons were spread throughout. But he also thought, with it being spread out, that it was so lightly packed that pretty much anything could pass through an atom if it were small enough. There was another scientist by the name of Rutherford. Right, we have an element named after him, Rutherfordium, who had a brilliant idea to test this theory. He figured, I will take something called an alpha particle, and it's what you get from a nuclear decay, and shoot it through the atom. With the expectation of a plum pudding model, all of them should have come out on the other side where he had a machine to detect them. And most of the time they did come out on the other side. However, on occasion, he also had another machine to detect it all around. It would come out that way, or this way, or bounce back that way. It would come out at various angles. What he discovered, or what he concluded from this, was that there actually must be some sort of mass in the center. It was only a small amount that got deflected. So he said most of the space must be empty, but a small amount of the space, must be taken up. And so he figured out it was taken up by the protons, and then later he discovered neutrons. So then we had our protons and neutrons in the nucleus with our electron cloud. This was, for a while, what we thought atoms were like, and it is pretty close to the truth. However, it's not all the way there. We would have two more models before we came to one that is pretty accurate most of the time. One quick example, the first one is the Bohr model. We are actually going to use the Bohr model a lot in this class because it is accurate enough that we can get important information out of it. It is missing a few key details, but it is still important as a simple way of expressing those things. So what we realized was not all the electrons had the same energy. And the way we discovered this was those spectra I mentioned. Actually, let me just look at a picture of them. Hydrogen spectrum. So a hydrogen spectrum looks like this. What it means is it emits light at this purple ray, this light purple ray, this blue ray, and this red ray. So around 650 nanometers, right between 450 and 500, so 460, 70, 80, about 485 nanometers, right? This is just above between 400 and 410, so we can say 405, and then we have this between 410, 420, 430, we could call this 435 nanometers. It's probably give or take 1 or 2 there, but this one isn't super precise, so it's a little hard to tell. Right, this one's right about like 655. I think this one's actually 657, technically. I'm trying to remember that one off the top of my head. It might even be 659. But anyway, these are all, no, that is, I think, 657. These are all of the different wavelengths of light given off by hydrogen. The question is, why does it only give off one wavelength? Well, why and how? And the answer to that is, or at least we thought at first, was the Bohr model. The Bohr model, I don't know why I drew this box, starts off with the nucleus. That has the protons and the neutrons. Let's not worry about that. And then it goes into different orbitals of electrons, or rather shells of electrons. We have a first shell, a second shell, a third shell, and we can pretty much go on. I believe in current year we have, let's see, well, there actually, it's the number of rows. 1, 2, 3, 4, 5, 6, 7 different shells. They also increase in how many can fit in how many electrons can fit in each shell. We start off with the first shell having 2 electrons. The second has 8 electrons. The third has 18, and the fourth has 32. After this, we haven't found, so there is another thing I'll talk about later in this lecture called orbitals that are needed for more electrons that we have not found. We have not found more orbitals to go above 32 electrons in a shell. That might be coming soon with the discovery of new elements. Sorry, bit of a yawn. So notice this first one goes up by 6 electrons, then it goes up by 10 electrons, and then it goes up by 14 electrons. So it increases by 4 every time. Well, kind of, right? 6 plus 4, or sorry, 2 plus 4, my apologies, sorry, I think I got it wrong. I'm sorry, like I said, my head is very tired today. So after the first jump, it goes up by 6. So it goes up by 4, right? 6, and then 10, and then 14. And that is not an accident, and we will get to that later. Again, if I'm seeming confused at any point, it's because I am ill. My apologies. So, the reason they thought this worked out is they realized whatever was causing that light to come off had to come from something, right? It was energy that was being given off, and it was a very specific amount of energy. So they realized that if they had these different layers and levels, they could set a specific amount of energy to be absorbed in one level to jump an electron up to be a higher energy electron. And then afterwards, it can come back down in something called relaxation. This is called excitement. Relaxation goes back down, and that is what gives off the light. A few places you can see this, right? Glow in the dark things. Fire. You put a lot of energy into elements with fire, and they give off light. Right? Fireworks are just different elements being burned. So this is the Bohr model. From this, we also discovered that they also add in order. So we start off with our nucleus, and then we have our first shell, or sorry, that probably just made no sense in the context. I'll ignore the add order. Second shell, third shell, let's call this other one a fourth shell. Electrons go into the lowest orbital first. The first one we found out can hold 2 electrons, or go in the lowest shell first, sorry. 2 electrons. After this, the next one can hold 8. We have 1, 2, 3, 4, 5, 6, 7, 8 spots here. I mentioned that the next one can hold 18. However, turns out atoms really like to have 8 electrons, and we'll explain why in the next chapter. Just know that 8 makes it happy in every row except for the first, where 2 makes it happy. It likes to have the outermost row be 8 electrons. The inner ones can have more, but it wants the outer ones to have 8. So we can do 2, 4, or 1, 2, 3, 4, 5, 6, 7, 8 here. That's not evenly spaced out at all, but whatever. And after we start this fourth row a bit, we can then go back in, right? And we can fill in more in here. You might hear my very sad daughter. Just ignore that. Right, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? It can get up to 18 here, and we're filling in more here, right? But it always needs 8 on the outermost. Well, it wants to get to 8 on the outermost. You can't go above 8 on the outermost one, so you need to fill in some of the furthest out one to fill in the inner ones more. So I won't go into the excessive details of why, because it is a little complicated, but we found out this works really well for predicting hydrogen, but every other element is a no-go. And so eventually we came to be what is one of the most important and correct concepts, which is orbitals. This one's basically like 99% correct, and to understand anything more complicated, you have to get a little more complicated. So actually, let me erase that first. Orbitals. We had to explain some weird things we were seeing. And we found out that we don't just have different shells of electrons, we have something called subshells, different layers within each of those shells, or different areas within each of those shells that electrons were different in. And I'll explain what I mean. We have 4 different types of these orbitals. S, P, D, and F. S orbitals all hold 2 electrons. P orbitals all hold 6. D orbitals all hold 10. And F orbitals all hold 14. Again, at most, it can have less. So this is the same amount that we saw our addition to. We start off on the first layer with only the s orbital, which is why we have 2 electrons. The second gets s and p, which is why it can have 8 electrons. It gets 6 plus 2. At the third, we get D in the picture with S and P for a total of 18 electrons. And then for the fourth, we add in F as well for a total of 32 possible electrons. And you can actually count this out directly in a row in the periodic table. So let's look and count out one of our lowest rows. And the F's include these ones down here. So let's see, the very first row has 1, 2. The next one has 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. After that, we have, right, going down a bit, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Total of 18 electrons. You will note that is not in the third row, that is in the fourth row. I will explain why that is the case. These ones are technically third row electrons, but I will, so when I said it, right, goes into the fourth row first, and it goes back into the third row, because it has to go into the outer one to fill the inner one more than 8, that's what I meant.